Good morning, everyone. Let's get started. So, today is we are going to do a generalization of what we had done last time, and this is going to be sort of the most important result that we would be using when we go to partial observability. Okay. So, what we had done last time was given a model M, and an approximate model M hat, I wanted to ask the question that if I find pi hat star, which is optimal for M hat, can I quantify what is the error that I get if I use this policy in the true model. Okay. Now, what we are going to do in today's lecture is look at the situation when the state spaces are different. Okay. So, going back to this quantization example, what we were doing was that we had a continuous state space, we discretized it, we solved the MDP in the discretized space, and we obtained a value function and a policy. Last time I had only talked about the value function, but what would also happen is that this is V hat star, we would also have a pi hat star, and I would like to understand what happens if I use this policy in the original model. Okay. Now, I am going to make one assumption in this. There are different ways to do. So, the issue now is when I have a different state space, I need to know how do I go from either the bigger space to the from the true state to the approximate state, or from the approximate state to the true state. Okay. There are different ways in which this can be done. I am going to focus on just one of them, and the idea is going to be I am given a function S, function phi, I am sorry, which maps from S to S hat, and I will call that state abstraction function. And in general, I will call this the true model, and I will call this the abstract model. Okay. This does not necessarily need to be an approximation. I am just looking at some different model. I am going to be solving things in this model and translating this back. Okay. Yeah. I will do my analysis for the case where it is finite. Really, nothing changes when they are continuous. Okay. No, cardinalities are different. Okay. So, I am assuming there are some different finite sets. If I am in the continuous spaces, the only thing which changes is I have to be slightly careful with some of my statements to ensure measurability. Beyond that, nothing changes. No. So, there are two ways. I can look at the inverse map from S hat to S. In the analysis that I am going to do, I will simply rely on this. Okay. So, the view that I am taking is I solved, let us go back to this quantization example. I solved it in the discrete space. I can't ask this question, right, because the policy pi hat star is a policy in the discretized space. I need a way to construct a policy in the original space, and the simplest way to do that is that if I have to choose at some time t, if I have to choose what to do at state S, I simply say I am going to quantize this state, and I will choose the action which was prescribed by the quantized state. What that means is that if I am doing this discretization of my grid, in all points which are in this grid set, I am going to be taking this action. In all points here, I will be taking this action, I will be taking this action, I will be taking this action. I'll be taking this section. Okay. For ease of notation, I'm going to write this as pi hat t composed with phi, and in generally I'll write phi is equal to phi hat composed with phi to mean that any component of this policy is the corresponding component of the hat policy composed with phi. So, the real question that I need to ask is that if I use this policy, what is the difference between the two? Okay, because that's the question where I will get a policy which is feasible in the original model. Any questions about the setup? Yeah. More or less, yes, but it's not exactly true. So, you see, the issue that is happening is I was implicitly exploiting the fact that these two are in the same space. There are certain intermediate steps which do not continue to work. So, what we'll do will exactly follow the outline that we had last time, but there are certain changes that will happen. Okay. That was the reason for me to do the, I mean, I could have followed an approach where we start with this model, take the special case when the two spaces are equal, and we'll recover the results of yesterday. But the point was, in yesterday's lecture, we saw what the main ideas are. We are now going to simply translate those to the case when I'm working on different state spaces. And the model that I want you to keep in mind is I can take any function f hat defined on the S hat space to any arbitrary space. I'll just say it R, but this could be on any space. So, think of this type of function defined at my quantization points, and I'm going to be working with the function f composed with phi. F composed with phi is going to be the piecewise constant extrapolation of this function. F hat composed with phi, right? It's going to be the piecewise constant extrapolation of this function that I start taking constant values in grid cells. Okay. This is still the case if both f and s hat are continuous, right? So, imagine the case where my original state space was 2-dimension and I project it into a 1-dimensional state space, let's say, which is the diagonal. I would still have that if there is a, so suppose there was something like this entire line now gets mapped to a point, I'm still saying abstractly whatever was the value of the f hat function on this point, it will take a constant value along this line. Okay. Now, what we did last time was we got bounds in terms of the soup norm. Okay. So, the first question I want to ask is, what is the relationship between, if I take two functions in the hat space, do the piecewise constant extrapolation of them, can I say something about the soup norm of these functions in terms of soup norms of the original function? Okay. So, let's think about it a minute, and can someone tell me what this should be? Yes, so this should be the same, right? This should be the same that I have in terms of the soup norm in the original space. And again, take this notion of piecewise constant extrapolation. All I'm saying is if I gave you two functions, so let's say the other function was maybe something like that, and I do piecewise constant extrapolation of this guy as well, and let me do this correctly, what is the difference between the straight line of the two, and clearly that is going to be the same as what was the maximum difference between the quantized functions. Okay. So, this is going to be a key step that I'll use in the analysis. Yeah. Oh, I'm sorry. This doesn't make any sense. Yeah, minus. Yeah. I'm So this would be less than equal to here. So I can have, I mean, for the analysis purpose, it does not matter, but it is possible that I have, so it doesn't show up in this quantization case, but let's say I have a function from 1 to 3. So phi takes from 1 to 3 to 1, 2, but phi of s is always equal to 1. Okay? So I can have an f hat function which differs in the second argument, but it doesn't show up in the range of phi. Right? So implicitly, I am always assuming that this is an onto function, and if this is an onto function, this would be an equality. Right? So that's, I don't remember now in the notes whether I say this explicitly or not, but in my head, it's always that when I'm talking about state abstraction, if some part of the abstract state is not reached, that's not a good feature mapping function, so I'm just going to be having an onto function all the time, in which case this would be an equality. It would be an equality. But either equality or inequality works for our purpose. Now, the key idea, so the questions that we ask are the same. I'm going to ask about policy error. I have to be now a bit careful in how I define policy error. Okay. Yeah. This would not be true if it is an arbitrary. No, I think all I'm saying is soup over all S f hat 1 of phi of S minus f hat 2 of phi of S is less than equal to soup over all S hat absolute value of f hat 1 of f hat minus f hat 2 of f hat. Right? This should be true all the time, as long as when I look at the range of this, that is a subset of the range of this. Right? That's all the statement is saying. So I'm interested in the same questions as before, but let's just think about what would policy error mean. Okay? Now the question in this, there are again different ways in which I can pose the question, because it depends on whether I take the policy in the original MDP or I take the policy in the abstract MDP. So before sort of going into this, there's always two ways to do this analysis, right? So what I am doing in the entire analysis is going to be, I take something in the abstract MDP and I lift it up into a function in the original MDP. The opposite way to do it is take any function in the in the original MDP. So I could have done the following also. Given any function in the original space and my quantization cell, I can construct a function which is piecewise constant here, some sort of average of the other function. Okay. And I could say what happens, relationship between the original function and that function projected onto the smaller space. Okay. The analysis is more or less in the similar style, but just in terms of time and sort of the application that I have in mind, I'm going to do the lifting part, that given something in the hat space, how do I lift it up in the original space, and not talk about given something in the original space and project it down to the hat space. Okay. So in that spirit, policy error then would be defined as given a policy pi hat of model m hat, So whenever I'm writing hat, that is of the model m hat, I can construct a feasible policy of the original model. Right? That feasible policy is going to be pi hat composed with phi, where the convention I'm following is pi hat is a time varying policy. I compose each component of that with phi, right? So the evaluation that I do in the hat model will be pi hat v hat of pi hat. Okay? And I want to compare it with what happens if I use this lifted policy in the original model. But I cannot compare these two value functions. This is on S space, this is on S hat. So if I want to do a fair comparison, this is the comparison that I would have to do. Right? What is the difference? So I'm interested in understanding. I found a policy in, I created a simulator of the system. I found a policy in the simulator. I ran it on the simulator, found what the performance is. And I want to know how well will this do in the true system. Okay? The true system has some different dynamics, but a different state space. So the question of interest should be, if I just do the piecewise constant extrapolation of what I constructed, how far it is from this. Okay? So I'm going to ask what happens in this lecture. As in the last one, we'll focus on the soup norm error between these two. And in the next lecture, we'll see if we can get sample path based errors rather than pointwise bounds rather than having soup norm bounds. Okay? Similarly, for value error, I have the optimal value function in the hat model, and so that's like the function we found here. If I solve the quantization thing, I do the piecewise constant extrapolation of that to get the function in the original space, and I ask what is the difference between V star and this. Okay. And finally, the model error question. I'm sorry? This guy? Yeah. Pi hat star will be V hat star, right? So I'm just saying, if I found the value, this is the same question I asked last time, right? I take my approximate model, I find a value function there, and I say, is the optimal value function here a good proxy for the optimal value function of the original model, right? So I'm not asking a different question as last time. Yeah.
So if we have, just out of curiosity, if we have the true value function in the true model, is that necessarily always the optimal model for the abstract model as well?
No, almost never. Okay, it's the same thing, right? I'm actually making no assumption about one of these being smaller than or bigger than the other, right? So if you, so in some cases, it may be, it's slightly counterintuitive, but in some cases it may be better to go to a bigger space, okay? If I can get some nice property. So imagine something like, when you'll have to make a made up model, but maybe I had some kind of a reflective Markov chain on a continuous state space. I can imagine a situation where instead of reflection, I assume it goes through. That gives me linear dynamics. Then I can have simplified dynamics in the abstract model, and that can be simpler to solve. Yes, but as I said, it doesn't really change much because so that only changes whether I have equality or inequality here. It doesn't really change anything else in any of the rest of the analysis that I'm going to do. So finally, the actual question of interest, which is the model approximation error. Right? So I find the policy pi hat star. I do the piecewise constant extrapolation of this to get a feasible policy in the original model. And I use that in the original model. And I ask how far off from optimal I am. Okay. So again, these are the same questions we asked last time, except I have to be a bit careful about which spaces I am comparing them on. These are not the unique ways to pose these questions. I just need some way of working in the same space. I could have projected this guy down to the hat space and said what the difference is and so on. But in some sense, this is the natural question to ask if I'm going to be using the policy of the hat model in the true model. What error do I get in the real world? I don't care about what's happening in simulation. Okay. The approach that we'll take is going to be the same as last time. Okay. So what we did last time was we defined a mismatch operator. We defined the error that if I take two value functions, one in the hat space, one in the original space, do a Bellman update of that, what do I get and what is the difference between the two. Okay. That's going to be roughly the same thing that we will pose this time with few small caveats which I'll explain as we go along. Okay. So the general notation is for all the operators, I'm going to be using hats to denote the corresponding operator in the hat model and without hat in the true model. Okay. So how do I define a mismatch Bellman operator? Okay. So when I was in the same spaces, I had defined the mismatch between taking any value function. This was defined as environment operator applied on V minus the approximate environment operator applied on V. Yes, so but now these are not on the same space. So first thing I have to actually see is what is the domain of D that I want to look at. Should it be value functions in the original model or value functions in the hat model? Mathematically, both things I can define in a valid way. As I said, I'm going to be focusing just on doing things in the hat model and lifting that up. So the way I'm going to be posing this question is ask about what to do with value functions in the hat model. So this has to be a value function in the hat model. But if this is a value function in the hat model, let me write it with some space so that we can add things later on. So if this is value function in the hat model, this guy will have to be the hat. This is okay. I can apply the hat dynamics operator on the hat model, but I can't apply this guy in the hat model. Okay. So I have to do a correction. The correction that I have to do is I have to lift this function up, and I have to see if I take a quantized value function, I do a piecewise constant extrapolation of that, do the dynamics update of that in the original model. How far it is had I done this in the hat model, but now this does not make sense because this is a function whose domain is the original state space and this is a function whose domain is the quantized state space. So if I want to make this comparison fair, I would have to take this and lift it up. Where the understanding is I'm going to be doing this first and then doing the lifting. Okay. So this is the natural translation of the mismatch operator on how it should be defined. Okay. Again, I could have done this the other way around also. I could have taken a function on the original space, projected it down and defined it appropriately, and that can be done, but we'll be focusing on just this one direction for this course. Right? So now, yeah. That quantized state is just because I have some dynamics in the hat model. For the purpose of getting these error bounds, I don't care how these approximate dynamics were found. Okay? There's some approximate dynamics, You made them up, you used some sophisticated technique to come up with that, doesn't matter. What will matter is what difference does those dynamics cause in terms of these things. And later we'll get IPM style bounds where the distance between the actual dynamics will matter. But I don't want to keep the, just one second, I don't want to restrict this to a specific construction of the approximate dynamics. We'll come back to quantization in the end, and we'll see how the bounds specialize for quantization, but I don't really have to derive everything just for quantization. Yeah.
Is there an advantage or a disadvantage to going one way or the other, going from the abstract skill set to doing one vice versa?
Depends on what you want to do, right? So there are some applications in which it may be better to go from the original thing to the quantized thing. In particular, as we did last time, right, when I said there are some instances where I want to get expressions in terms of mismatch operator of V star rather than V hat star, right? So the way I'm starting the construction now, I'll never be able to talk about the mismatch operator of V star, right? So if I wanted to do in some learning setting where I want to use concentration inequalities, this is harder to work with than the other direction. Other questions? Okay. So the basic result that we had last time was the one-step propagation, right? One-step error propagation. We have to be a bit careful with this now. Yeah. This guy is, so this is a function which takes a value function in the hat model and gives me a Q function in the true model. So one-step error propagation, I'm going to pose it as follows. Okay. Just let me make sure I do it. So if I take a value function of the true model and an approximate value function of the hat model, I construct Qt plus 1 to be equal to the environment update of Vt plus 1, and I generate Q hat t plus 1 to be the environment update of V hat t plus 1. Can I say something about the error of these two? Okay. So what I would have to obtain is Q t plus 1 minus Q hat t plus 1, and I'll ask this question. If I lift up the approximate Q function to the bigger space and just notationally, so Q hat composed with phi evaluated at S and A is equal to Q hat of phi of S and A. Right? The action spaces are the same, so by this notation I mean it's only lifting up the first argument of the Q function, not both arguments. So I want to ask what happens to these guys, and my bound is going to be that this depends on the mismatch operator applied on V hat t plus 1 plus the error between V t plus 1 and V hat t plus 1 lifted up. In the special case when S and S hat are the same, so phi is identity, this reduces to the relationship that we had derived last class. Okay. And now this is somewhat natural. What this is saying is if I take something in the hat model, a value function in the hat and V, and look at what happens, sorry, there's notationally I should have been calling this Qt's, not Qt plus 1. So I take a value function in the hat model and the true model, do one-step environment update of these, and see how far these guys are. That's going to depend on how far they were originally, plus something which depends on how different these two environments are in terms of the mismatch Bellman operator. Okay. And the proof is similar to last time. So, what we will have is we are looking at ET applied to Q minus E hat T applied, ET applied to Vt plus 1 minus E hat T applied to V hat T plus 1 composed with phi. And I want to exploit the fact that the environment operators are non-expensive. That was the basic property we had last time. So, I am going to add and subtract. So, remember what we did last time. I could have either added and subtracted E hat V or E V hat. In this case, in the direction in which I am going, I only have one option. So, I am going to say this is less than equal to E t of V hat T plus 1 extrapolation minus E hat T V hat T plus 1 plus E t V t plus 1 minus E t V hat T plus 1 composed with phi. Okay. So, I am adding and subtracting this term on both sides. And this completes the proof, because the first quantity is by definition the mismatch Bellman operator, and the second quantity is the same environment operator applied on two functions, and from non-expensiveness of E t, I get the second term there. Okay. And now that I have the one-step error propagation, rest of the analysis is straightforward. I am just going backwards over time to get an expression. There is one part I have to be careful about, but other than that, it is just going to be backward induction. Any questions? All right. So, let us look at policy error. Let us derive it directly, and then we will write down the okay, let me just do that. Okay. So, I am going to define as before alpha pi t. This is the V. So, I am looking at the setting where I am given a pi hat, and I am looking at the evaluation of that policy in the true model minus V hat pi hat composed with phi. This is I am going to call alpha pi. Beta pi t is the same thing with q. So, q pi hat composed with phi t minus q hat of pi hat t composed with phi. Okay. Now, last time we had shown that alpha, this should be alpha pi hat. Alpha pi hat t is less than equal to beta pi hat t, and my claim is this is going to be less than equal to tau equals to t to capital T, the norm of the mismatch Bellman operator of V hat pi hat t plus 1. Okay. Last time we had this was less than equal to minimum of two terms, because the other guy was going from the evaluation in this guy to projecting down, but we are not doing that here. Okay. Now, before proving the whole thing, let's just look at the first inequality. When these were on the same space, that was equivalent. Now, this is not clear how whether going from this to this is the same. Okay. So, I will first prove the first inequality, and then we will prove the rest by induction. So, I know that this is just some policy, right? V pi hat composed with phi t. This is equal to the policy evaluation operator of pi hat t composed with phi applied on qt pi hat composed with phi. Okay. While v hat pi hat t is the operator in the hat model, pi hat t applied to q hat pi hat t. So, the difficulty that I have in this case, which was not present in the same state spaces case, is that these two operators are on different spaces. So, although these operators were non-expensive, because they are on different spaces, I cannot directly say that this guy is going to be less than equal to this guy. What's going to happen here is something interesting, and it helps if I write this down explicitly. Okay. So, let me write down V t pi hat composed with phi evaluated at some point s. This is equal to V of this is equal to qt of phi pi hat t of phi of s, sorry about that, s pi hat t of phi of s. Okay. This is saying I am going to look at the q function in the original model, q function of pi hat composed with phi. This is q function at some s and a, and the action that I am going to pick is going to be the policy pi hat t applied to the quantization of the state. This guy is a function of s hat, and this is equal to q hat pi hat t of s hat and pi hat t applied at s hat. Okay. So, let me now look at the lifting that I am doing here. Okay. So, let us see what is v hat pi hat t composed with phi evaluated at s. This is going to be equal to q hat pi hat t of t phi of s pi hat t of phi of s. Okay. Now, let us compare this guy and this guy. Okay. They are choosing the same actions, right, and their domains of the first component is different. So, by definition, this object is equal to q hat pi hat of t composed with phi. Remember, when I compose something with phi, I get only affects the first component of this, not the second component. And the second component is the operator of pi hat composed with phi applied there. Right? The action that I pick is according to this policy. So, I get that this object is actually, I can compare these two things. Right? So, here I could not, but if I look at this guy v hat pi hat t composed with phi, that is going to be t pi hat t composed with phi applied to q hat pi hat t composed with phi. Okay. So, this looks a bit messy, but it's sort of saying something fairly simple. And what that means is that if I now want to find the difference between this guy and this guy, I have a situation where I'm applying the same action selection operator on both of them. And therefore, I can use the fact that this operator was non-expensive to say that this would be less than equal to the norm between q t and q hat t composed with phi. So, I get the first part, that alpha pi hat t was less than equal to beta pi hat t. The rest is simply backward induction. As usual, I'll start my induction argument at capital T plus 1, where the statement is vacuously true. I'll assume that this is true at t plus 1, and I have to show the result at time t. And the result at time t is simply saying q t pi hat composed with phi minus q hat t of pi hat composed with phi is less than equal to, this is exactly this setting. I get the mismatch operator at time t plus the forward future errors which I have computed. Okay. So, this ends up being the mismatch operator on v hat pi hat t plus 1 plus alpha pi hat t plus 1, and that completes the proof. Okay. So, the whole thing required a bit of notation and so on, but the overall expression for bounding this error is relatively straightforward. Once we have this, the value error is going to be very, very similar. With the value error, I'll define alpha star t to be equal to v star t minus v hat star t composed with phi, beta star t to be q star t minus q hat star t composed with phi, and I'll claim that alpha star t is less than equal to beta star t, which is less than equal to summation tau equals to t to capital T, the mismatch Bellman operator applied on v hat star t plus 1. It's the same argument as before, but I'll have the same issue as in this work. Right? So, notice that in the star model, this will be T star, this will be T hat star, and I have to show that something like this would hold. Okay. Roughly the same argument is going to work. If you remember how we had shown the contractive property of T star by taking the optimal at 1 and showing that I have an inequality that way, I can follow the same type of an argument to show that this equality holds. And once I have this equality, the other one is just the one-step lemma. Okay. So in the interest of time, I'm not going to do the detailed derivation of these things in terms of stars, but really the argument is this is minimization over all actions, and if I take a specific action, I'm going to get inequality. And I can do that here because notice that in the model, I had kept the action spaces the same. If I look at a model where I'm also changing the action spaces, deriving this will require a little bit more effort. But since my action spaces were same in both cases, this part is straightforward in this model. So finally, we get to the model approximation error. And in the model approximation error, I am going to ask what happens to V pi hat star composed with phi minus V star. As before, I am going to use the triangle inequality. I'll use V hat phi hat star composed with phi plus use the fact that this guy is optimal and I have obtained the bound on the first one and a bound on the second one. The bound on the first one is going to depend on V hat pi hat star, which is same as V hat star. So I simply get this is less than equal to twice summation tau equals to T to capital T, the mismatch operator applied on V hat star T plus 1. And as in the last class, this thing has the nice feature that, so how do I use this bound, right? I did something in the approximate model, found out the optimal policy, and I found out the optimal value functions. If I have the ability to compute the mismatch operator, then I can compute this guy, and I have a bound on what my model error is going to be. Okay? It requires me the ability to do one model update in the original model. I want to emphasize something here. So for those of you who have seen discounted cost models, let's just think a bit in terms of what would happen if I had discount. So all discount means is that future is discounted by some amount, and when we are doing the one-step update, I'm going to get a discount factor term here. So in the discounted model, this would be the future discounted sum. Now in the RL literature, the way a lot of the approximation bounds are derived, so like what I want to emphasize here is that this bound compared to the value error bound does not have any time expansion. This is simply a multiplicative factor of 2. In the RL literature, they derive these bounds in a slightly different way in the discounted setting, and there is a multiplicative factor of 1 upon 1 minus gamma. And the reason they get that is that they are deriving, so recall last time I had derived this other bound in terms of dV star. If I tried to derive a bound in that style, I would get that linear dependence on time. Okay? The nice thing of getting bounds in terms of V hat star is that model error is just twice the value error. Okay? So this is something which is to keep in mind if you are doing some of this thing. So in our paper on this thing, we could show that a lot of the existing results, you could tighten the analysis simply by using this slightly tighter bound than the bound which is typically used in the literature. Okay. Now, the drawback of this is the same drawback that we had last time. This requires me for this I need the ability to do one update in the true model. What if I do not have that? I know that my approximation or whatever is within some epsilon delta ball of the true model, but I don't know, I don't have the ability to do that update. Then I can use IPM style bounds to upper bound the mismatch operator. The catch is I'll have to now be careful in terms of how do I define model error, because these things are over different spaces. Okay. So we'll follow what we did last time, and I'll start with the definition of model error. Again, there is no unique way of defining model error. I'm giving this definition because it is tailored to the type of analysis that I am doing. If I was doing the analysis which takes something in the original space and projects it down, my model error would have to be defined slightly differently. So I'm going to say, given an epsilon and a delta, both greater than equal to 0, m hat is an epsilon delta approximation of m. If, let me write these things in full first, and then I'll write it in the compact notation. So first property that I want is that when I look at the cost for any state and action, and I compare this with the cost that I will get in the approximate model, this should be less than equal to epsilon t. Okay. This is equivalent to saying that Ct minus C hat t composed with F is less than equal to epsilon t. The second part is somewhat different. What I'm going to, so you see now the difficulty with the second part is that the original model has dynamics which takes S and A and take it to the S space. The other thing has dynamics which start from S hat and A and take it to the S hat space. So first I have to fix whatever I'm conditioning on. So it will have to be of a form where I say the distance, some IPM distance between, we'll fix this, but I'm just sort of giving the idea. I'll have to say something between S and A and some version of phi hat t. This part I can fix the same way as I fixed in the cost, right? I can say that distance between some measure conditioned on S and A and this other measure conditioned on phi of S and A for all F and A should be less than equal to delta, right? That's the nature of the thing that I should get. The difficulty is this part is now on S space and this part is on S hat space. So I need to figure out a way to put this in the right space, and the idea is you take whatever measure you get here and you project it to the S hat space. That's the way I'm going to do. And the reason I'm projecting it down to the hat space is because my mismatch operator is defined on the hat space. I want to do things in the hat space. So I need something here which will be on the hat space. I'm going to, just for the ease of notation, call this phi t, and I'll define what I mean by this here. And what I mean is that p phi phi of t of any point S hat conditioned on S and A is the probability of phi inverse of S hat conditioned on S and A. So, this is a measure from S cross A to delta S hat, and the comparison that I am doing of the probabilities is in the S hat space. For those of you who have seen this, this is sometimes known as the push forward measure when we are working on these types of things. Okay. All right. So, just to complete this, I should say, if I am writing it like this, for all S and A, this thing should hold. So, I have now the translation of model error to this space, and recall what we had done in the case of same state spaces. I had argued that mismatch Bellman operator could be upper bounded by something which depended on the model error. Right? If I can do the same thing here, then I'll have the result for rest of the things where I am getting bounds just in terms of model errors and parameters of the system, right? So, let's try to derive that. So, I want to look at the mismatch operator for some function V hat, and recall that this was equal to the model operator applied on V hat composed with phi minus the hat model operator applied on V hat composed with phi. Okay. And I now want to massage it in a way that I can get terms in terms of the model errors. I am going to write this out in full just because that would be slightly easier to see what is happening. Actually, let us see, I have that in the notes. Let me write it in full, right. So, I could have done the following, but it is just going to be, remember that E t of V was C t plus P t of V and so on. So, we can use this type of notation and get the result also. I think it will be slightly clearer if we take a bit more tedious route. So, I am going to write this thing as follows. This is C t of S A. Let us write it for a particular S A, and we will take the supremization over S and A later on. So, let us look at C of S A plus summation over S prime P t of S prime given S A. So, what will happen here is, sorry, I should have done this. Let me write this again. This is V hat composed with phi. This is okay. I'm getting confused. S prime P t of S prime given S A V hat of phi of S prime. This is the first thing, right? I take the environment operator of the original model. It is just the value function which is V hat of phi of S prime. The second guy is going to be, so you see, I will have the operator applied here, and wherever F hat was coming, that should be replaced by phi of S. So, this should be C hat of phi of S and A minus summation over S hat prime P hat t of S hat prime given phi of S and A hat prime. So, from triangle inequality, I immediately see the first term, which is going to be epsilon t. And now I have this guy, but the difficulty here is this is dynamics of the original with this guy. I have to massage this a bit to get it in the, actually no, sorry, this is, okay. So, triangle inequality says this is equal, less than equal to epsilon t, which is c minus c hat. Let's look at the other thing and see what is happening. And I'll go back to this quantization example. What I'm saying here is sum over all the values in F space. So, I'm going over all the points here, and I am integrating a function which is piecewise constant. Right? If I'm integrating a function which is piecewise constant, I can change this summation. So, I can write it in the following form. I can write it as all summations of S hat prime. I go over each one of these cells, and within each cell, I go over all S prime such that phi of S prime is equal to S hat. Right? I am changing the sum over this by breaking it down into two parts. And now notice what's going to happen with this guy. This is always phi of S hat here. Right? So, what I get is this object, this is S hat prime, and this object becomes equal to summation over S hat prime p phi t of S hat prime given this was here phi of S. So, phi of S and A sorry, this is S and A. I got confused with the wrong one. S and A V hat of S hat prime. Okay. So, I get a expression. So, this integration of a piecewise constant function is same as averaging the measure and then doing the integration. So, I get this and the other term. So, this whole thing will be less than equal to epsilon t plus delta t times rho f of V hat. So, I get the similar result as last time, that the sup norm of the mismatch operator on any value function in the hat domain is the error between the costs plus delta, which is the error between the dynamics defined in that specific way, times the Minkowski functional of my value function that I was taking here. Okay. This will mean that if I go to all my results, but let's just do this for model approximation, this guy is going to be less than equal to twice summation tau equals to t to capital T epsilon t plus delta t rho f of V hat star t plus 1. So, in case I do not have the ability to run the mismatch operator on the true model, but I know the distance between the original and the true model in terms of the errors between the cost and the error between the push forward of the dynamics of the original model and the dynamics of my abstract model, I can give an upper bound on the model approximation error. Okay. As was the case for last time, this bound is somewhat loose. The looseness of the bound is coming from this part, the triangle inequality here, and the looseness is coming, there is a looseness in the one-step error propagation analysis also, and when we go to IPM style bounds, that leads to a further looseness factor also. So, these bounds tend to be somewhat loose, but they are still giving us at the very least they are providing continuity, which says if my abstract model is getting closer and closer to my true model, then my error is going to disappear. Questions on this? Okay. So let's try to see if we can use this to say something about quantization. That was kind of my motivating example on what do I do with different state spaces. So let's try to see if we can point out something about quantization. And intuitively, as someone had mentioned when we had discussed this last time, if I want, so what I would like to say is, at the very least, as the number of quantization cells grow to infinity, the error goes to 0. Okay. In order to do that, I need to assume some sort of smoothness in my properties, right? If my cost function was something which was changing erratically, so suppose I had a cost function which took value 0 on all rationals and value 1 in all irrational numbers. Okay? I can't expect that to have a smooth approximation. So I'll have to make some assumptions about my function being smooth in some sense in order to get some approximation errors. So we are going to make the following assumption, that my model M, C and P are Lipschitz. So that means I'm implicitly assuming my state space has a metric on the state space. This is a metric space. Cost is Lipschitz means that if I take the cost of any state S1 and action A minus cost at state S2 and action A and look at the distance between them, there is some universal constant LC. These could be time dependent, which is going to depend on distance between S1 and S2. Actually, for the purpose of this analysis, let me just assume there is no dependence on time, so that what we are writing is somewhat cleaner. Okay. So I'll not write time dependence on these guys. P Lipschitz is a bit tricky. I need to decide what metric am I going to impose on the probability spaces, and we are going to work with Wasserstein distance. So we are going to assume the following. If I look at the Wasserstein distance between the dynamics that I get if I conditioned on S1 and A, and the distribution that I get if I conditioned on S2 and A, that is less than or equal to some constant LP times the distance between S1 and S2. So if I have a specific model, I can check these things. What this roughly is saying is, if I take a cost and I move the state a little bit, my cost should move a little bit. Okay? And if I take my dynamics and I move the state a little bit, my cost should move a little bit. Okay? So it's a natural thing in any physical system. I typically expect the cost and the dynamics to have these type of smoothness properties. Note that I am not arguing if I change the action a little bit, my cost changes a little bit. In terms of actions, I can have jumps, but just for every action, the dynamics should be smooth in this. It doesn't really matter. I'm assuming discrete just for the ease of writing. For continuous, the reason I'm not doing this for continuous is to make the statement precise, we have to impose certain assumptions and it becomes a bit tedious. But there is really nothing in the analysis that we did so far which relied on discreteness of A explicitly. Okay? The assumptions which you would require if you go to continuous is, I want to make sure that pi hat star is a measurable function, and I need to impose certain assumptions on the dynamics to ensure that dynamic program has a measurable solution, and I'll have to assume phi is a measurable map. In cases, the other thing I should mention is, in case my cost can go, in case my state space is unbounded, either discrete or continuous, and my cost is not uniformly bounded, I also have to worry about expectations being well defined. Right? I can get plus infinity, minus infinity type of things to have expectations are not well defined. So, when you are in non-finite spaces, you will also have to impose some assumptions to say the cost functions lies in some L1 space or so on. But apart from these standard assumptions, everything works. Okay. So, now what I want to do is, in this, coming back to this, we are assuming this is there. Recall how we had defined quantization. So, my quantized model C hat at any S hat and A was really C of S hat and A, because S hat was one point in my quantization cell, right. And the way we defined P hat was, I said P hat of some S hat I given S hat or S hat j given S hat I and A is going to be the dynamics of going to the entire cell corresponding to this guy conditioned on S hat I and A. And I would now like to argue, I would like to compute what is the model error between this approximate model and my true model. Okay. Before that, I want to sort of emphasize one part which is important. Recall our definition of delta. So, what I had done was, delta was distribution between two measures defined on the hat space. Okay. So, when I am working with Wasserstein distance, the metric would be on the hat space. So, I need some metric on the hat space in order to use this bound, and I am simply going to say my metric on the hat space is that distance between S hat of a point S hat I and S hat j is just the distance in the S space between S hat I and S hat j. Okay. This is the natural metric that I can have in the hat space. Okay. So, this in particular means that when I talk about the if I am using Wasserstein distance, this Minkowski functional will end up being the Lipschitz constant of V hat. This is Lipschitz constant on the discretized space, not the Lipschitz constant on the continuous space. That is important because the piecewise linear extrapolation of my function is like this. This is not Lipschitz continuous, but the function in the hat space with the distance metric given there is Lipschitz continuous. Okay. So, that was also another reason why we wanted to define this metric in the hat space rather than in the original space, because in the original space I lose Lipschitz continuity. Okay. So, first thing to observe is, let us look at the worst case distance between C and C hat composed with phi. Okay. So, I am going to make an assumption, and my assumption is that when I do this quantization, this is always the center of my code cell, and this distance is going to be less than equal to r for all code cells. So, I will assume that there is a radius r, and all my quantized cells are when measured from the center, the distance is less than equal to r. So, when I look at this quantity, this is really looking at the distance between C of S and A minus C hat of phi of S and A, which is equal to C of S and A minus C of phi of S and A, because I had defined C hat to be the cost at that point, and by the Lipschitz continuity property of C, I will get this is less than equal to the Lipschitz continuous constant of C times the distance in the S space between S and phi of S, which will be less than equal to LC times R. So all this is saying is, if I have a smooth cost function and I do quantization where quantization cells do not have a radius greater than equal to R, then distance between the smooth function and its quantized value would be less than equal to the Lipschitz constant times R. Okay? So I get a bound on epsilon t. Let's look at delta t now. So for the delta bound, I have to look at P phi t. I'm going to give this result rather than derive it. Sort of, as I'm looking at my proof, I realize right now that this relies on the primal definition of Wasserstein distance, which we did not discuss. And it's going to take a bit of time. I don't think it's super important for the central point that I want to make. So let me just give what delta t would be, and delta t is going to be greater than equal to LP plus 2 times R. Okay. What really is happening is, you see, what I have to do is the measure between this guy and P hat of phi of S and A. And notice that this guy, the way I had defined it, is really equal to P phi t on this given on phi of S and A. So the distance is in terms of what measure do I get on the code quantization cells if I start from a play point S or I start from a point which is slightly less than S. Okay. And I want to relate it to the measure I get at a single point. I know that is smooth. So the trick with the difficulty only is that I'm not computing Euclidean distance, I'm computing Wasserstein distance. And for Wasserstein distance, there is a way to get things in terms of distance of the original spaces using the primal definition, and that's what the analysis in the proof uses. But I can get this type of bound, and if I substitute, if you just trust me for this derivation, if I go back to this analysis, what I will get is that this is less than equal to tau equals to 2e to capital T LC plus LP plus 2, the Lipschitz constant of V hat star T plus 1 multiplied by R. Right. So what I am getting is that the error depends on how smooth the dynamics are. How smooth the cost is, how smooth the dynamics are, how much variation do I get in the quantized value function that I computed, and how big my quantization was. So it's quite natural to see that I will get a result in this form, and it has the nice property that if I say I keep on doing smaller and smaller quantizations, then this error will continue to go to 0. So this shows that sort of I can use this idea to derive bounds which are in terms of properties that I can compute. So if I was interested in things like how many quantization cells do I need in order to get a good approximation. In sort of what we did not do yesterday, I had said that as we derive bounds on the span norm of a value function, we can derive bounds on the Lipschitz constant of the value function. And I can use those types of things to say, here is an upper bound on the Lipschitz constant of the value function, and therefore how small r should be, so that this entire thing becomes less than whatever approximation error I want. Okay. So we can, with these results, we can answer the basic questions that we were interested in. The only caveat is in all this discussion that when you take, if I do the following experiment, I take a model, a small scale model, I say discretize it very, very finely, and I compute what is almost the exact value function, and I do a coarse quantization, compute this quantity based on the fine quantization to get the value function, and numerically compute this bound. We will find that this can be very, very small when this number is very large, okay? Or even this number is large, or even this number is large, right? So there is typically about a factor of 2 up to a factor of 10 difference in what this quantity is versus what our bounds are giving us. So what we are going to do in next class is revisit our entire calculation and ask, so you see the errors are coming because of triangle inequalities at different places. I'm going to ask, can I not use triangle inequality? And the way not to use triangle inequality is not to use norms. If I had done this entire analysis without using norms, I would have gotten equality. Okay? So we are going to go and do that. Some of our analysis will change because I'm using properties of norm to simplify some of the things, but we will get a almost the same derivation with expressions which are of this type but do not involve norms. Okay? And then we'll see that what happens to deriving upper bounds and so on, and we'll do that discussion next class. So I think I'm done a little earlier. We can stop now, but sorry, you have a question.
Except for the quantization thing, is there any other examples where like state spacing, true model and the abstract model which we are going to write are different?
Yes, any place where you are doing reinforcement learning using neural networks. Right? Whenever I'm doing RL on neural networks, so typical RL architecture, this is one version of that. I have a representation learning block, and this is sort of the way RL literature says is that this is a common thing, and I have two heads. There is a value head and there is a policy head, and you are doing maybe typically some kind of a softmax here, and I'll do some policy gradient thing fed back here, some type of TD loss being fed back here, and I'm learning all of these things. If I look at the output of this representation layer, that is the state abstraction, right? I've taken something from my original space, which could be images or whatever. I've constructed this as an abstract space, and I want to see whether this is a good abstraction from the original thing or not. Okay? Now, what's happening in RL is that you are not explicitly learning dynamics and so on. So I can't directly take these bounds to derive bounds in that setting, but I could ask the question that how good this representation is. After the fact, can I try to learn dynamics from this? Or there are papers which say you try to learn dynamics in parallel with this just to improve my representation learning, and that improves the type of approximation that we are doing. Okay? Phi is the representation here, right? And what we are going to do probably second lecture tomorrow is that when I go to learning in partially observable settings, I'll have to do some kind of recurrent representation here, and whatever is happening in any learning algorithm in partial observation is also using some kind of state abstraction. So the way we are going to look at POMDPs is rather than traditional approach which looks at belief states and so on, I'm going to say that I can build any approximation of a POMDP as long as it's an approximate model M hat which satisfies model approximation properties like what we discussed here. And if I have that, I can do dynamic programming in POMDPs, and that will give me some approximation thing. And on Friday, we'll come back to this looking at certainty equivalent policies in POMDPs, and we'll see we can use these types of bounds to get bounds for certainty equivalence. Yeah. You mean you mean these two? I don't need all of that. This is one choice that I'm making. I'm just saying in quantization, this is the simplest way I can do quantization. Okay? Yeah, in the quantization, I'm saying this is what I'll do. I'll just say I'll take the value at the quantized cell and I'll do this type of thing, right, as we discussed yesterday, right? I can do quantization in other ways also. I can do piecewise linear interpolation. I can do fancier things. Your bounds will improve on those. The analysis will become a bit more detailed, right? So I'm just doing this for the simplest possible setting. Yeah.
So all of this is level of states. If you extend this story to actions,
Mm-hmm.
would any of this dramatically change your?
In the discrete world, if I give you a mapping from actions in the bigger space to the smaller space, and I need to figure out what will I do when I get a policy in the abstract space, how do I interpolate it back? Depending on what you pick, like people give different type of notions there, but as long as I have an inverse mapping as well, I can derive bounds. Okay? In continuous state spaces, things are slightly more delicate because if both spaces are continuous, I need some kind of I need to ensure measurability in some sense, so there's a bit of that. But conceptually, nothing changes if I have action quantization also, provided I have a way to go back. And the hard part in action quantization is really how do you come up with a good action quantization scheme. And when I'm doing these IPM style bounds, these will be a bit more involved because I have to abstract out both states and actions. Right? So when I was doing things like C of SA, it would be things like minus C hat of some abstraction function which takes both S and A and gives me a S hat and A hat. So at that level I can work, and then what people do is essentially in infinite horizon settings, if I get a policy in the hat model, I can do things like the occupancy measure of that policy and then translate that to the original model, which gives me a more reasonable policy than directly translating things. So there are some nuance involved in transforming policy. The type of bound we are deriving would roughly remain the same. Yes. Yes. Yeah. Yes. Yes, there's two. This is very, very bad. Right? So you see, I wanted smoothness here. This 2 is precisely because of that, because I could have gone slightly on, one could have gone on the left and one could have gone on the right. And now in my, so you see, what ends up happening is this was my boundary, this is one center, I take a state here and a state here, and now I'm comparing dynamics from these 2 points. That's the reason I'm getting this 2R distance here. So that's the place where it reflects. And if you look at type of typically you want this Lipschitz constant to be less than 1 by gamma or something like that. And this part makes it a bit harder. Right? So that's where it is showing this junk in this discreteness of my quantization. Right? Had I done a smoother quantization, so then something like first order hold, this would have been much, much smoother. But then I have to, my analysis would have to be done slightly more differently. Computing this epsilon t and delta t require a bit more work. All right, so we are out of time, so let's stop and we'll start in half an hour. All right, let's get started. So, what we are going to do right now is try to get sample path bounds on approximation error. Okay. So far I have been focusing on bounds which are computable. Okay. Our analysis was very straightforward. It gives us computable bounds, but the bounds are loose. Now, we are going to take the other approach. I am trying to get the tightest bounds we can get from the style of analysis that we are doing. Okay. And these bounds will end up being non-computable in the sense that it will depend both on what is happening in the approximate model and in the true model. And then we will try to see, can we take this tightest possible bound expression and get bounds on these bounds to get things which are computable. Okay. So, I will start with the simpler setting. So, I have a model SAPCT and I look at an approximate model, same state spaces, different dynamics and costs. And for the first part, I'll get bounds on policy error, which will be, if I have access to both models, this bound is computable. I'll get bounds on value error, which will not be computable even if I have access to both the models. It can be fixed, but I'll not go it right now, just in the interest of time essentially. And I'll combine them to get bounds on the model error. And I'll show how I can get bounds which are computable when I have access to both models. Okay. That's going to be our first step, trying to get as good approximation bounds as we can get if I have access to both models. Now, we'll follow the basic style of analysis that we have been doing. I'll look at the mismatch operator. So, dt of v was Et of v minus E hat t of v. But what we have done so far is I have been trying to take the soup norm of this and get bounds of the soup norm. I'll not take the soup norm, I'll try to get bounds without taking the soup norm. Okay. And for that, notationally, it is recall the definition of our operator Pt, the script Pt, where Pt of v gives me a Q function, which was so this thing evaluated at some S and A is summation over S prime Pt of S prime given S A v of S prime, right. So, this was my linear operator, which takes a value function and gives me a Q function. So, I will start with few observations. The first observation is, if I take two functions v1 minus Et applied on v2. So, in the soup norm case, I had shown that this thing is a non-expansion in the norm. I do not want to take the norm. So, what happens to this? This is really Ct plus Pt of v1 minus Ct minus Pt of v2. So, this is equal to Pt of v1 minus v2. Okay. My calligraphic P and regular P look the same, but hopefully it will be clear from context. Okay. So, what we had done last time was essentially this thing is true, and when I take the norm, I get the norm of this multiplied by Pt, and since Pt is stochastic, I got 1. Right. So, I have the same, like last time we were taking a upper bound on this, but this is an exact expression. Now, let us look at the one step propagation error. So, my setting is I am given two value functions v and v hat, and I define q to be equal to the environment operator applied on v, q hat to be the environment operator of the hat applied to v hat, and I want to get what is q minus q hat. In the old setting, I was trying to get a norm on this, and we had shown that the norm on this was a mismatch operator plus the error between v and v hat. Okay. Let's look at it without taking norms, but using the same idea. So, I will look at q minus q hat. This is equal to E t of v minus E hat t of v hat. And I will use the same intuition that I used in the triangle inequality for the type of bound that I want to get is I will add and subtract something to make sure that I get something like a mismatch operator. So, the difference is now I don't have absolute values. So, this will be an exact calculation and not an inequality. And I just have to make sure I do it in the right order. So, I will do E hat of E t of v hat minus E hat t of v hat plus E t of v minus E t of v hat. Okay. I have to be careful with the signs now because there is no absolute value. What I am doing is I am adding and subtracting these terms. Now, the first object is a mismatch operator. So, this is dt applied on v hat, and the second object based on what we had shown earlier is the dynamics operator applied on v minus v hat. So, this is the per step generalization of the soup norm bound. Remember, in the soup norm, I was taking the soup norm of the left hand side. Triangle inequality gives me that is less than the soup norm of this plus the soup norm of pt multiplied by this, which is less than equal to the soup norm of the error. If I don't take the soup norm, the advantage is I get equality rather than inequality. The drawback is that I have to work with the dynamics of the error. Okay. There is an analog version of this which will require the mismatch operator of v times something. I am going to focus on this version of the bounds simply because as we did last time, I want to see what can I do when I do the approximation in the hat model. Okay. Now, what we did earlier was once I had the one step error propagation, rest of the analysis was trivial. That is no longer the case because now we are not taking norms. So, let us see the simpler case what happens for policy error. So, I am going to overload the notation that we had used last time. So, the setting is I am given a policy pi. This is same policy in the, it is a valid policy both for hat and M model. And I am going to define alpha pi t of S to be equal to v pi t of S minus v hat pi t of S. In the soup norm analysis, I was defining a constant to be the norm of the difference of the functions. In this case, I am defining a function which is the difference of these two functions. And I am going to define beta pi t of S and A to be equal to q pi t of S A minus q hat pi t of S A. In the soup norm case, I was showing, so essentially what we were defining there can be thought of as norm of alpha pi and norm of beta pi. Right? and we had shown norm of alpha pi is less than norm of beta pi because the dynamics operator was non-expensive. While in this case, I can write b pi alpha t is really the action selection operator of pi t applied to b pi t, right? Or sort of in expanded form, this is q pi t of s pi t of s minus q hat, let's just write it in terms of beta, I don't need to do this. It is beta pi t of s pi t of s. But I have this relationship between going from difference in q functions to different in value functions. Okay? And now I'll sort of write the proof here first and then we'll write the statement. Also notice that beta pi t, which is this object what I did in the one-step error, should be equal to the mismatch operator applied to v hat pi t plus 1 plus alpha pi, plus the dynamics of alpha pi t plus 1. Right? If I unroll this, I get basically the error bound, but I am going to take these things in terms of these two recursions. I'll write it here just so that we have both together. So I can get an exact expression for what is the error between the value functions and q functions of the same policy. And this is in terms of mismatch functionals of the solution to the hat model. But when I do the propagation in the of the v errors, that has to be done with respect to the dynamics of the true model. So this is not a computable bound, but there is no approximation here. This is the exact policy evaluation. For those of you who are familiar, this is similar to what would be called a simulation lemma in reinforcement learning. Okay. So, and I can get my older bounds once I take norms. All we were doing in the earlier case, when I take norms here, this guy was non-expensive. And when I take norms here, I was using triangle inequality and the fact that norm of pt times alpha is less than equal to norm of alpha. Okay. Any questions? Okay. So again, this is not computable because one, I have to do one operation in d pi for everything, but more importantly, I have to do this dynamics. Let's now look at the value error. And this is where things get a bit tricky. Now, the trouble with the value error is I'll have the style in which we are doing analysis, I'll get an inequality, okay? Because let's recall what we did there, right? So I'm going to now say alpha star t of s is equal to, let me just write it in vector form now that the notation is clear. Alpha star t is equal to v star t minus v hat star t, and beta star t is q star t minus q hat star t. Okay. And now I require two things. I want to know what is the relationship between beta star t and alpha star t plus 1. So note that just from the one-step error, I know beta star t is equal to the mismatch operator applied on v hat star t plus 1 plus alpha plus pt times alpha star t plus 1. So this part is easy from my one-step propagation error. The tricky part is getting an expression for alpha star t in terms of beta star t. Okay. I'll not be able to get this in an exact manner. I'll try to get a bound on this. So let me explain that. So let's look at v star t of s minus v hat star t of s. And I am going to assume that the optimal action here is A and the optimal action here is A hat. That means that this quantity is equal to q star t of S and A minus q hat star t of S and A hat. Okay. Again, my assumption is A is the optimal action at S and A hat is the optimal action at S under the hat model. Now, I can get an upper and lower bound on this quantity. The upper bound works by saying, well, I could have taken q star t of S and A hat. A was the optimal action. If I change this to a suboptimal action, my q function will increase. And this object really is equal to q hat star of S and so this, let's write this as beta star t of S and A hat, and if I just write what A hat is, this is beta star t of S and pi hat star t of S. So I get an inequality which says alpha star t is less than or equal to the operator pi hat star t applied to beta star t plus 1. This is a pointwise inequality. I can also get a lower bound by the same argument. Okay. So I could have done v star t of S minus v hat star t of S with the same notation is q star t of S and A minus q hat star t of S and A hat. And now what I am going to do is replace this action A hat with A. Since A hat was the optimal action here, if I replace it with a different action, the q function will increase. And if q function increases, but this is with a negative sign, I will get a inequality with the other direction. This is greater than or equal to q hat star t of S and A minus q hat star t of S A, which is going to be equal to beta star t of S pi star t of S. So combining with the other quantity, what I get is, let's write this here, this is one equality, and I get that the operator t pi star t applied on beta star t is going to be a lower bound on alpha star t, which will be an upper bound on t pi hat star t beta star t. Okay. So what I am saying is, the reason I was saying earlier this is not computable is the above equality is only true if I know the exact alpha star t. but these bounds do not give me exact alpha star t. It gives me a range between alpha star t should lie, and to find the actual alpha star t, I would have to know the value functions. So this is not a computable bound. It's just a bound which is true, but I cannot use this even if I had access to both models. Unless I solve the value function in the true model, I cannot use it to compute things. Okay. There is a way to do computations based on this bound, though. Okay. I'll just explain the idea here, but we'll use that idea when we actually do things in the model approximation case. So you see, these are all pointwise inequalities. So if I wanted to get any type of bound, I can do the following. Suppose I get expressions, let's call them alpha, for now alpha t and beta t, and I want to ensure that alpha star t is less than equal to alpha t and beta star t is less than equal to beta t. Suppose I wanted to get bounds on these objects which are computable. My claim is I am going to write a sequence of inequalities. If those inequalities hold, then these things will be valid upper bounds on the quantities of interest. Okay. So the relationship that I am going to write is beta t is less than equal to the mismatch operator of v star v hat star t plus 1 plus pt applied to alpha t plus 1 and alpha t. Just want to be careful. Let's just do it this way. Suppose I do these computations. Okay. My claim is that this guy will be greater than equal to beta star t, and therefore this guy will be greater than equal to alpha star t. Okay. So I can get computable bounds provided I get things which are upper bounds on these things. So you see, I know this is in between that. If I take alpha star t to be equal to its upper bound and take that, substitute that thing back in here, what I'll end up doing is getting upper bounds on these quantities rather than sorry, so this I'm making a mistake here. This has to go this way. So let's explicitly write it in this way. Yes, and this is the only operator that I'm using. It's a linear operator, therefore it's monotone. Right. So what I can do is, if I can find any method to get an upper bound on this, this can hold with equality and this can hold with equality, I'll get an upper bound on the whole thing. Okay. So this is going to be my general idea. So you see, this tells me first how I can get upper bounds. By a similar thing, I can get lower bounds, but it also tells me what's going to be my general approach to get computable bounds. Because right now this is not computable because it requires the dynamics in the P model. If I have the model approximation thing that P and P hat models are close to one another, I can relate dynamics in P model with the dynamics in the P hat model with some IPM distance. So I can use something like that to actually get computable bounds. Right? Is this part clear to everyone? Okay. That's going to be our big conceptual leap in this case, which allows the sample path analysis to work. So basically, given a policy, I can do exact calculations if I have access to both models. I still just need to solve the value function in one model. And I can get an upper bound by doing these two things exactly, as long as I have ability to do this. And by doing to get the lower bound though, I need to know the optimal policy in the true model. All right, now let's look at model error. So for model error, I am interested in V pi hat star t minus V star t. Notice I already know this quantity has to be greater than equal to 0, because I am comparing performance of some policy with the optimal policy. So I am going to write the triangle inequality, but since I don't have absolute values, this is going to be equality. This is V pi hat star t. Let's see, I have to get it in the right thing, minus V hat pi hat star t plus, this is, rather than writing it as plus, I will write it with minus. Let me write that and I will explain why I am writing it with minus. Okay. So I am subtracting the same term in both sides, so it should be clear this is inequality. Okay. The reason I am writing it in minus is because the bounds that I had derived were V in a true function minus V in the hat function. So I want to keep both of these things in the same form. Okay. So I know how to compute this guy. This is an exact evaluation that I can do with the policy error terms. This I am not sure how to get, but I know ways to get an upper bound and a lower bound on this. Okay. So I am going to now do the following calculations. I am going to argue, going to compute a alpha positive t and beta positive t, which are going to be upper bounds on this guy, and I am going to compute alpha negative t and beta negative t, which are going to be lower bounds on this guy. Okay. And once I subtract them, I will get an upper bound on my value error. That is my basic idea. Okay. Sorry? Yes, I have exact for the first term. I want to write it in terms of upper and lower bounds, because later on I want to get rid of this p dynamics. So I want to say as long as this is holds with an inequality, things will be fine, and when I get rid of this with the p dynamics, this will hold with inequality. Right. So what I want is beta plus t to be greater than or equal to dt of v hat star t plus 1. Notice this was v hat pi hat star, but I can take it d hat star because the policies are the same, plus pt of alpha upper bar t, and I want alpha upper bar t to be greater than equal to the operator corresponding to the pi hat star t policy, applied to beta positive t. This is the same style of getting upper bounds on the policy error as I had described here to get for the value error. Okay. If I take upper bounds of this exact expression, these will be upper bounds on alpha pi hat star and beta pi hat star. Okay. So, in particular, this implies that alpha pi hat star t is going to be less than equal to alpha plus t. Okay. Is this part clear? What I am going to do for the other guy now is beta minus t is going to be less than equal to dt of v hat star t plus 1 plus pt of alpha minus t plus 1 and alpha minus t to be less than equal to t pi star t applied to beta minus t. Recall that in the lower bound of this object, I have the star guy of the true model. So, this is not good. I need to know the policy of the true model. Nonetheless, if I am able to compute this, I can show that this implies that alpha star t is lower bounded by alpha minus t. So, combining both of these, I will get that this object is less than equal to alpha plus t minus alpha minus t. So, this is a in principle bound, because to compute this bound, I need the ability to do dynamics in both the true model. I need the ability to compute this guy, and I need to know the optimal policy. So, it is not very usable, but my claim is that this is the tightest type of bound that I can get with the style of analysis that I am doing. Right? In particular, if I had access to both models, I can make these two guys equalities. I can make this guy an equality, and this is the only place I will have an inequality. Okay. Even if I knew the true model and I take this as equality, this bound will not be exact, because in this bound, this is the source of inexactness, right? So, it depends on how much did the optimal action in one model differ from the optimal action in the other model. And whenever we have that these things differ a bit, I will get I am not quantifying what that error is, I am simply saying there will be a upper or lower bound on that, right. So, there is still going to be some error in this, but I have removed all traces of errors that were coming from triangle inequality. Okay. In particular, this was the biggest source of error in the previous analysis, the triangle inequality that I was using in the model error setup, and that has gone. I do not have a good way of bounding this, but I have some expressions which will give me some type of bound on my model error. And what I am going to do in the rest of the lecture is try to make sure how can I get this to work. Okay. So, I have to understand what do I do with this guy, and I have to understand what do I do with this guy. If I can handle these two cases, then I have a working upper bound. Any questions? Because I am doing expectations. You see, so let me take this guy. Okay. Suppose I am interested typically in an application, I'll be interested in what is this value error at the beginning, right? So if I unroll this from the beginning, what I'm really saying is this can be written as summation of the expected values, so of these guys plus the expected value of this guy, right? So I'm doing averaging over the sample path, and that's why I'm calling it a sample path based bound. I mean, I don't know. We decided to call it sample path based bound when we were working on it. You could have called it expectation based bound or pointwise bound or whatever. So there's no no deep reason for using sample path sort of. When we were thinking about this, it was really trying to go back to how can I get rid of the errors that are being induced by the soup norm, and we were thinking of this as I'm keeping track of what's happening along the sample path rather than just the soup of the difference of value functions. Other questions? Okay. Okay. So let me say something about this object, because this is the bigger source of concern as it requires me to know the optimal policy, right? If I knew the optimal policy, I don't need to do any of this. I'll just implement the optimal policy. So everything else I can live with. This kind of just is something which clearly I don't have access to the optimal policy if I'm trying to do all this analysis. Okay? So what can we do? So what's happening here is, let me write this explicitly, saying alpha of S should be less than equal to beta minus t of S pi star t of S. Okay. Suppose I know that there is a set, let's call that C of S, such that pi star t of S belongs to C of S. And this is in general a subset of the set of action spaces. Okay. Then I could simply choose one possibility for choosing alpha t of S is equal to minimize over all actions in C of S beta minus t of S and A. Okay. Ideally, I want C of S to be just a singleton which contains the optimal policy, but I don't have this. But in many applications, I know the range of the optimal action, which might be less than the overall range of all things. But in the worst case, I'll just take the entire action space. Okay. So this gives me now, if I replace this with this recursion, I get a computable bound. I still need to do dynamics with P, but ignoring that, I don't need to know the policy. All I need to know is that there is a set of actions which contains the optimal action. Okay. So if you are doing things such as inventory management, we can oftentimes bound what will be the range of actions that one would pick. In other applications also, depending on the underlying dynamics of the system, you may be able to say certain set of actions are always bad, right? So at a particular state, I don't need to look at different types of actions. Maybe some actions are going to be suboptimal, and I can drop that, and I just do optimization over a smaller set. Okay. So this is one way. Worst case, replacing this with the set of all actions, that I can fix this. So what I'm now going to focus on, what about the P dynamics? Before that, actually, let's spend some time here to see how does this relate to the bounds that we had so far. So, one thing that I could do is, let's go back here and say what happened if I took the absolute value. Okay. So, I'll try to compute a class of bounds in which, let's say, alpha plus is equal to some alpha, which is equal to minus alpha minus, and beta plus is equal to some beta, which is equal to negative of beta minus. So, I'll try to get symmetric bounds on alpha and beta, and that would immediately mean that this is less than equal to twice of alpha. Okay. This is the flavor of bounds that we had obtained when we were taking the soup norm. Okay. How do I get bounds which are symmetric? So, I would have to ensure that these two guys hold with equality. So, to get symmetric bounds, actually I do not need equality since the signs are different. I can do the following. Let us say beta t is greater than equal to absolute value of the mismatch operator applied on v hat star t plus 1 plus pt applied on alpha t, and I will ensure that alpha t is greater than equal to the max of t pi hat star applied on beta t and t pi star t applied on beta t. If I ensure both of these things, I can show that this guy satisfies this dynamics, and it also satisfies this dynamics, and I can show negative of that guy satisfies this dynamics and also satisfies this dynamics. Okay. So, this gives me symmetric bounds, and this will imply that 0 is less than equal to v pi hat star t minus v star t is less than equal to twice alpha. What we had done in the sample path bounds was that we had taken, this is still pointwise, these are still functions, right. In that case, what we did was we said alpha t is going to be some constant times the identity function, right. I tried to get a uniform upper bound on this, and when I try to get a uniform upper bound, we reduce to the soup norm bounds. Okay. If I do not take the uniform upper bound, I take any upper bound which can vary according to state, but if symmetric, I will get these types of symmetric bounds. But what we really are doing is getting bounds which where the upper and lower bounds are different. So, this I need to, so the trade off is in this analysis I need to keep track of 2 recursions to compute the bounds. I can get a single recursion and get a loser bound, okay. But this is, I am losing quite a bit because I am taking maximum of both of these quantities, while in the other case I was selectively in the positive direction choosing something different, in the negative direction choosing something different. This forces me to take the worst of the 2. So, it gives a symmetric bound, but it will be a much weaker bound. Okay. So, now let us go to computations. So, for computation, as I have mentioned, if I take this guy, then the only non-computable step of my analysis now is doing this PT business. So, I am going to say, let me assume that m hat is an epsilon delta approximation of m, but I am going to relax what I mean by epsilon and delta. So, in the past epsilon and deltas were constants, I am allowing them to be functions of state and action. So, I am going to say I have an lower bound epsilon minus of S and A, which is less than equal to C of S and A minus C hat of S and A, which is less than equal to epsilon plus of S and A. And I am going to write this compactly as epsilon minus is less than equal to C minus C hat is less than equal to epsilon plus. I am just stating that. Let us go ahead and you will see. Okay. Because you see, I have one is an upper bound and one is a lower bound, right? So, I will have to get an upper bound for this dynamics, and I will have to get a lower bound for this dynamics. Let me complete it and we can check. Now, I am also now going to define delta of SA, and these could be a function of time. This is the IPM distance between the dynamics given S and A and the dynamics in the hat model given S and A. Now, note that in contrast to what we were doing in with epsilon, this will be a symmetric bound, right, because I have a metric. This is a metric, so this will be this is a symmetric bound, while here I was taking different upper and lower bounds. I cannot do that with the IPM distance. Now, the key observation is that we had this IPM inequality, which was summation of over S, P of S given S prime given S A, V of S prime minus summation over S, P hat of S prime given S A, V of S prime is less than equal to delta S A times the Minkowski functional of V with the absolute value here. Okay. That means without the absolute value, this is less than this and greater than equal to negative of this. So, this means I am going to get, let me write this as P hat T applied to V minus delta minus rho f of V multiplied by delta is less than equal to Pt of V is less than equal to P hat T of V plus rho f V applied to delta. Okay. Here I am treating delta as a SA valued function. So, what I can get is that I can upper bound these dynamics with the dynamics in terms of hat, and I can lower bound these dynamics with the dynamics in terms of hat. So, if I make that appropriate change in my recursions, I will get bounds which are computable. Okay. So, what I would have to do is I will say beta plus t is greater than equal to dt of v hat star t plus 1 plus p hat t of alpha plus t plus rho f of v hat rho hat of alpha plus t times delta, and beta minus t is less than equal to dt of v hat star t plus 1 plus p hat t alpha minus t minus rho f of alpha minus t times delta. Okay. It's still not completely computable because I have to get this mismatch functionals, but I have gotten rid of the dynamics in terms of the dynamics in the hat model. Okay. So let's now look at the last remaining thing, which is this D guy. So recall that D of V is equal to E t of V minus E hat t of V. This is equal to C t plus P t of V minus C hat of t minus P hat t of V. So this is going to be less than equal to epsilon plus rho f of V times delta. And by a similar argument, I can show that D of V is greater than equal to epsilon minus plus rho f V of minus rho f V of delta. Okay. So if I have upper and lower bounds on the difference of cost functions, and I have the IPM distance as a function of state and action, I can get upper and lower bounds on the mismatch operator. Okay. I substitute these things back in here and I am done. Okay. So now my bounds have loosened a bit, but everything here is computable except for this part, right. So this is the only non-computable part that is left, and in the worst case, I am going to take this to be equal to the set of all actions if I have no structure about my model, and these are the tightest possible computable bounds that I can get with this style of analysis. Okay. To get anything tighter, I would need to identify some relationship between pi star and pi hat star. So far, I am just saying there is arbitrary policies. In some systems, you can say certain changes in the model will mean that my policy should not change by more than a certain amount, and then I can get terms which depend on the distance between pi and pi hat star. But unless I do something like this and I just follow this basic style of argument, these are the closest possible, the tightest possible bounds that I can get and compute. Okay. Questions? Not with equality. So what we have done is you can take examples, but this guy, where is the thing? So this I can do with equality, but I'll not be able to do this guy with equality, right? Because I'm taking the IPM bound if I want to do the dynamics with p hat. So this would never be with equality. But numerically, what we have observed is that these bounds are, if I do the bounds with the true dynamics of the system, then this is almost overlapping with the actual thing. So these are almost exact, because what happens in a lot of real systems is when you make a small change in your model, your optimal policy changes by a small amount. So all of these things are the error that we are getting in replacing the optimal action at 1 with a slightly suboptimal action. Those errors are small, and everything else is roughly the same. Okay. Once you start doing replacing these guys with the upper bounds and replacing this with the upper bound, you start introducing some errors, but these are typically of the order of twice the, if I look at the actual error, this is roughly twice of that. So it's not super bad, it's reasonable. Okay. This also sort of, this type of bound that we had earlier, it's also worth thinking of other things that one can do. So in the literature, there are some types of bounds where we try to get weighted norm bounds. So you see, what we are doing is roughly we have a bound which is a function some a which belongs to the V space. That's the type of bound that we have, that we get that V pi hat star t minus V star t is going to be less than equal to 0 and alpha. What we did earlier was saying, I am going to say this is going to be less than equal to some constant times 1. Okay. And I also have the bound which is 0 is less than equal to q pi hat star t, q pi hat star t minus q star t is less than equal to beta, and we were trying to get this to be less than equal to a constant times 1 also. Okay. We can try to get something which is better than, it's somewhere in between this and this. So one type of bound one can try to get is, say, that beta of S and A should be less than equal to some weight function W of S, right, times a constant, let's say, right. So rather than keeping this constant times no dependence on state and action, I say I'm allowing my bound to vary according to the state, but not vary according to the actions. And if you make this type of substitution, you can simplify some of the calculations, and I can sort of get coarser bounds at the advantage of having simpler computations. Okay. But I'm not going to go into detail here. What I want to spend some time discussing is, how does all of this work if I was working on different state spaces? Okay. So what we did in the previous lecture. And conceptually, it's once I figure out how the one-step argument would work, rest of the thing is going to be roughly the same when we are working with different state spaces. So there is, I'll not go over the derivation. Let me explain what is happening, and I'll spend some time explaining how to do computations in that setting, because that's going to become important when we go to POMDPs. So what do I do when I have model approximation or state abstraction, sorry. So the setting is, I have a model on some state space, and I have an abstract model on some abstract state space. In this case, the mismatch operator that we had defined took a hat value function and gave me a true model skew function. And this was equal to the dynamics of the true model applied on V hat composed with phi minus the dynamics of the hat model applied on V hat and doing a piecewise constant extrapolation of this. Okay. So, what ends up happening when I do the one step error thing? So, one step error propagation. So, now I am taking some value function in V, some V hat in V hat. I am defining Q to be equal to the environment operator applied on this, Q hat to be the environment operator of the hat model applied to V hat. And I want to look at the error between Q minus Q hat composed with phi. Okay. In last lecture, I started talking about the norm of this object. Right now, I will not talk about the norm. Okay. Same as what we did earlier in this lecture, let us look at this without the norm. And what is going to happen with roughly the same analysis is that this is going to be dt of this plus the p dynamics applied on V minus V hat composed with phi. Okay. So, this gives me, if I know the error at this step, how the error is going to go back. So, with this, rest of the analysis will remain roughly the same. I will have to be defining things in terms of these types of errors. So, if I am interested in policy error, what I know is I have a policy pi hat. I am going to take the policy which is pi hat composed with phi, and I am going to ask what is the difference between V applying on pi hat composed with phi minus V hat of pi hat composed with phi. Okay. Again, this is the same object we talked about in the previous lecture. In the previous lecture, I was taking norms. Now, I do not want to take norms. So, this guy is going to end up being less than or equal to, or let us see. So, we are going to call this alpha pi hat t, and I will define beta pi hat t to be equal to q pi hat composed with f at t, these should be with t, minus q hat pi hat at t composed with phi. And we will have the recursion beta pi hat t is equal to dt applied to V hat pi hat t plus pt of alpha pi hat t. This recursion is coming from the one step dynamics. So, this looks the same as what we had without model approximation, except that now I am defining errors a bit differently. And the other part will be the same. What will end up happening, let me write it in the full form rather than the operator form, because the operator form is not as transparent. So, this is what I get when I get from beta to alpha, and note that this other thing is equal to simply saying alpha pi hat t is the operator in the true model of the policy pi hat composed with phi at time t applied to beta pi hat t. So, this ends up being the same expression that I had last time, except I have to carefully keep track of how I am going back and forth between different spaces. Okay. So, same thing is going to happen in the value error and the model error. I want to focus a bit on how will we get computable bounds in these settings. Okay. So, I do not want to go ahead and write all the expressions for value error and policy error. They are going to be similar structurally. I just have to add these compositions at appropriate places. Okay. What I want to do is focus on computations. And as we did in the first half of this lecture, there are two sources where things are difficult. One is some of the expressions will require me to know the optimal policy in the true model, and that I am going to replace in the same way that I did here. I will do minimization over some set which contains the optimal action, possibly the entire action space. So, I am going to focus on the dv hat computation and the pt of alpha computation, because these are the two steps where we need things to be done slightly better. And now, the thing is, so I am going to get my bounds in the following form. So, when I am doing model approximation, I really do not want to get bounds in the F domain, because my whole point was that I have difficulty doing computations in the F domain. So, I am going to make assumptions of the following type. There is E epsilon lower bar and epsilon upper bar, which belong to the Q function of the hat model, such that epsilon lower bar of phi of S and A is less than equal to C of S and A minus C hat of phi of S and A is less than equal to epsilon plus of phi of S and A. So, epsilon lower bar ends up being constant for all states which map to the same quantized value. Okay. So, I will get this type of uniform bound, and I will get so remember my function here was the df of p of phi t given S and A and p hat t given phi of S and A. Right. I am going to ask for a delta phi of S and A. I am going to ask for a delta function which also depends on phi of S and A. So, these things in general will be a function of S. I take the worst case over all S, which give me the same quantized value, and I get these uniform upper bounds here. Okay. Once I do something like this, the recursions that I am going to get are going to be completely in the hat domain. So, I do not have to do any computations in the original domain. I can do computations in the hat domain. So, let us look at that. So, first let us look at this object. So, let us look at d of v hat at some S and A. This is equal to C of S and A plus summation over S hat P T of S prime given S and A times V hat of phi of S minus phi hat of phi of S and A minus summation over S hat P hat T of S hat prime given phi of S and A minus V hat of S hat prime. This is S prime. Okay. This is what my mismatch operator is. And note that I can upper and lower bound this term with terms of epsilon plus and epsilon minus. So, let me show the upper bound, lower bound will be similar. This is going to be less than equal to epsilon plus of phi of S and A. And the other object, as we did while deriving the previous bound, this is piecewise constant over all values which get the same S hat. So, this object is going to be upper bounded by the IPM distance, which itself is upper bounded by some function of phi of S and A. Sorry. Phi of S and A times rho f of V hat. Okay. The lower bound will be similar. So, what I am trying to do is I am trying to get upper and lower bound which are uniform in S hat rather than S. And once I get that, this will be the type of computations that I can do because this is in my approximate model and I know how to do computations in my approximate model. This requires me to know something about my model differences so that I can compute this. Right? So, I am willing to spend a bit more effort to get a bound here. To get a coarser bound, like had I taken that to be state dependent, these bounds would have been tighter, but I cannot do computations in the S space. So, that is why I am trying to get computations in the S hat space. Does that make sense? Okay. Same thing will hold with Pt of alpha, and let me show that. So, I know that when I am doing any calculation of Pt with respect to some function which is V hat composed with phi, minus the computation in the hat model with V hat composed with phi, this is upper bounded by delta t of phi of S and A times rho f of V hat. And this is by definition of my IPM distance. And therefore, when I am doing computations with respect to Pt, I can replace that with computations in the other model. So, what I am trying to do is, for this to work, my alpha function should be piecewise constant, right? So, I will try to get bounds which will be of the form alpha plus hat, which is belongs in V hat, and I will try to set alpha plus t to be alpha hat plus t composed with phi. And I will do the same thing with beta. I will get a beta hat plus t, which belongs to q hat, and I will set beta plus t to be equal to beta hat plus t composed with phi. So, in order to get these bounds, I am getting upper and lower bounds which depend on just this guy I am keeping measurable with respect to the hat model, and that ensures that I can get bounds in my calculations. So, some expression of this form for every S and A here this will only depend on phi of s. So the trick to doing computation with this model in the hat model is that I get upper and lower bounds of my cost, which are uniform, and I get bounds on the IPM distance, which is an upper bound on the true IPM distance, uniformized over all states, which gives the same thing. And then I can keep track of these alpha upper bounds and lower bounds, which are piecewise constant. So effectively, I can just do the computations here, and I get my error bounds in terms of alpha hat plus composed with phi. Okay. Does this kind of make sense? So I know there are a lot of details, but I wanted to provide the main idea here, because the details are just going to be, you now plug all of these things together and we'll get lengthy looking expressions, right? But the key thing to realize is with these things, I can have a exact model, an approximate model. I need to know the model distance in terms of these epsilons and deltas, and everything else is computations being done in the abstract model. I'm not doing any computations in the true model beyond this minimization over pi star, which I'm upper bounding by some set where the optimal action lies. So if I have a specific model where I'm doing a specific type of an approximation, we can do these types of function calculations and see the type of results that we get. Okay. So oftentimes these calculations will be done on model specific things. So if I'm doing quantization, I'll try to get these bounds in a tighter manner for quantization. But if I'm doing other approximations, like the example that I had given in the first lecture, there is some distribution which is correlated. I'm assuming that that distribution is independent. What happens to the thing? I'll try to get these errors in terms of making things simplified or taking a smaller state space and exploiting the properties of the approximate model, and then use these bounds. Okay. Any questions on this? All right. So where do we go next, right? So far we have primarily focused on what happens when I have full state observation. What I'm going to do in the next 4 lectures is look at what happens when I have partial observations. Okay. And there are 2 main ideas that will be there. When I have partial observation, I can always treat, so let's recall what we did with full state observation, right? I said I can have the entire history of observations and actions that my decision maker has observed as a state, and I can do dynamic programming in terms of those histories. That remains true with partial observation as well. If I have histories of observations, I can always do dynamic programming with respect to histories. It does not matter whether these histories of observation were of the full state or some subset of the trajectories of random variables which have been realized so far. Then what we did was I identified conditions under which, when I have a state space model, I can get a much simpler dynamic program. It's the same thing in the partially observed setting. I'm going to give sufficient conditions on what is called an information state, so that when I have an information state, I can do a dynamic programming. And in the next lecture, we'll see multiple examples of how I can construct a information state for partial observations. For those of you who have seen some material on POMDPs before, the most commonly used information state is the belief state. But the point that I want to get across is I don't care about the belief state. As long as I have an information state, things work. Okay. So now the thing comes, how do I do approximations? Approximations will mean if I want to do any computation, I want to construct an MDP like approximation which is close to the POMDP. So what we'll try to ask is, can I construct an MDP which is close to a POMDP? Closeness means in terms of these model distances that we are talking about. So, what we did in the earlier lecture today, how do I compare two MDPs which are defined on different state spaces? That's exactly what's happening in the partial observed setting. I have one MDP which is defined as the history as the state, and the other MDP which I am constructing as an approximation, and I would like to get approximation bounds. So, once I take this view, all the bounds are just corollaries of what we have done. Okay. It's going to be the similar type of expression that we will get what happens in the case of PO-MDPs. We can get soup norm bounds, we can get sample path space bounds. Okay. So, we'll look at PO-MDPs in details in the first lecture tomorrow, look at the approximation bounds in the next lecture, and on Friday I'll talk a bit about certain specific types of approximations for PO-MDPs. Right. Any questions on any of this? Okay. If not, then let's stop here.